Hey, science fans! Welcome to another exciting episode where we unravel the mysteries of the universe. Today we're diving into the fascinating world of steam power and the Clausius Rankine Cycle. This cycle is a cornerstone in the field of thermodynamics and plays a crucial role in how we generate electricity. The Clausius Rankine Cycle is like the engine that drives many power plants around the world. It's an essential process that converts heat into mechanical energy, which is then transformed into electrical energy. From coal to nuclear to solar thermal, they all rely on the power of steam to generate electricity. Each type of power plant has its unique way of harnessing steam, but the underlying principles remain the same. You might be thinking, steam? Isn't that a bit old-fashioned? Well, it might surprise you to learn that steam power is not only relevant, but also incredibly efficient and versatile. But trust me, it's incredibly important. Steam power has been a driving force behind industrial advancements for centuries and continues to be a vital part of modern energy systems. The Clausius Rankine cycle is a fundamental process in thermodynamics, the science of heat and energy. Understanding this cycle helps us appreciate the intricate balance of energy transformations that power our world. It's all about using heat to create steam, then using that steam to spin turbines, and finally generating electricity. The process involves several stages, each critical to the efficient production of power. So buckle up as we explore the four main stages of this remarkable cycle: pumping, heating, expansion, and condensation. Each stage plays a pivotal role in ensuring that the cycle runs smoothly and efficiently. Get ready for a wild ride through the world of power generation. We'll delve into the science behind each stage, uncovering the secrets of how we turn heat into electricity. Stay tuned, and let's embark on this electrifying journey together. Our journey begins with liquid water. This seemingly simple substance is the lifeblood of countless industrial processes. But to harness its full potential, we need to manipulate its pressure. We need to increase its pressure to get things started. By doing so, we can move water through various stages of processing and transformation. This is where the pump comes in. Pumps are essential in many industries, from power generation to water treatment, ensuring that water reaches the necessary pressure levels. It's like the heart of the cycle, pumping water from a low-pressure state to a high-pressure state. Without this crucial step, the entire system would come to a halt. Think of it like squeezing a water balloon. When you apply pressure, the water inside is forced to move and change its state. The pressure inside builds up. This buildup is essential for the water to be effectively utilized in subsequent processes. Higher pressure is crucial for the next stage of the cycle, heating. When water is under high pressure, it can absorb more heat energy, making the heating process more efficient. This pumping stage requires energy input to make it work. Pumps are often powered by electric motors or other energy sources to ensure they can generate the necessary pressure. It's like giving the pump a little push to get the water moving with enough force. This initial push is vital for maintaining the flow and pressure throughout the system. Now, you might be wondering why we need to increase the pressure in the first place. The answer lies in the efficiency and effectiveness of the entire process. Well, stay tuned to find out. We'll delve deeper into the reasons behind this crucial step and how it impacts the overall system. With our high-pressure water ready, it's time to turn up the heat. The water enters a boiler, a giant vessel designed for heating. Inside the boiler, things get really hot. The heat source can vary. It might be burning coal, nuclear fission, or even concentrated solar energy. No matter the source, the goal is the same: to transfer heat to the water. As the water absorbs heat, it undergoes a remarkable transformation. It changes from liquid water to steam. You know, the same steam you see coming from a boiling kettle, but on a much larger scale. This steam is now ready to do some serious work. The high-pressure, high-temperature steam we created is ready for action. It enters a turbine, a device with blades mounted on a rotating shaft. Think of it like a giant fan. As the steam expands through the turbine, it pushes against the blades, causing the shaft to rotate. This rotation is what we've been working towards. It's mechanical energy, the kind that can power generators. The spinning shaft of the turbine is connected to a generator. The generator converts this mechanical energy into electrical energy, the kind that powers our homes and cities. So, the steam has done its job, but what happens to it next? Let's find out. Section 5, Stage 4, Cooling down with condensation. After expanding through the turbine, the steam is at a lower pressure and temperature. Now it's time to convert it back into liquid water so we can start the cycle all over again. This is where the condenser comes in. It's a heat exchanger that removes heat from the steam. The steam, carrying much less energy, condenses back into liquid water. This condensed water is then pumped back to the boiler and the cycle begins anew. It's a continuous process of heating, expanding, cooling, and pumping, a symphony of energy transformation. Section 6, Efficiency Boost Ultra-Supercritical Power. Now let's talk efficiency. Not all Clausius Rankine cycles are created equal. Some are more efficient than others, meaning they can generate more electricity from the same amount of heat input. Enter ultra-supercritical power plants. These are like the Formula One race cars of the power plant world. They operate at incredibly high pressures and temperatures, squeezing every last drop of efficiency out of the cycle. By increasing the temperature and pressure of the steam, these plants can achieve efficiencies of up to 45% or even higher. That means they convert almost half of the heat energy into electricity, which is pretty impressive. Section 7. Challenges and solutions keeping things running smoothly. While the Clausius Rankine cycle is a marvel of engineering, it's not without its challenges. Like any complex system, things can go wrong. One challenge is droplet formation in the turbine. As the steam expands, it can cool down and form tiny water droplets. These droplets can erode the turbine blades, reducing efficiency and even causing damage. Corrosion is another concern. Impurities in the water can cause rust and other forms of corrosion, weakening components and shortening their lifespan. To tackle these challenges, engineers have come up with clever solutions. Water treatment systems remove impurities, while advanced materials and coatings resist corrosion and erosion. Section 8. Innovation for efficiency, squeezing out more power. The quest for higher efficiency never ends. Engineers and scientists are constantly pushing the boundaries of what is possible, seeking new methods and technologies to extract more power from the same amount of fuel. This relentless pursuit is driven by the need to reduce emissions, lower costs, and meet the ever-growing demand for energy. Engineers and scientists are constantly exploring new ways to improve the Clausius Rankine cycle. This thermodynamic cycle is the backbone of many power generation systems, and enhancing its efficiency can lead to significant gains in power output and reductions in fuel consumption. One approach is to increase the temperature and pressure even further, pushing the limits of materials science. By developing new materials that can withstand these extreme conditions, we can achieve higher efficiencies and greater power outputs. This requires extensive research and testing, as well as collaboration between material scientists, engineers, and industry experts. Another is to utilize reheating, where the steam is heated multiple times during the cycle. This process helps to maintain the steam's energy, allowing for more efficient power generation. Reheating is a well-established technique, but ongoing innovations continue to refine and improve its effectiveness. Regenerative feedwater heating is another innovation that recovers heat from the steam, improving overall efficiency. By preheating the feedwater before it enters the boiler, we can reduce the amount of fuel needed to generate steam. This not only boosts efficiency, but also reduces emissions and operational costs. And of course, advances in turbine and boiler design play a crucial role. Modern turbines and boilers are designed to operate at higher efficiencies, with improved aerodynamics, better materials, and more precise control systems. These advancements help to maximize the power output while minimizing losses and wear and tear on the equipment. By constantly innovating and refining this remarkable cycle, we can generate more power with fewer emissions, making our energy future brighter and more sustainable. The integration of renewable energy sources, such as solar and wind, into the power generation mix further enhances the potential for efficiency and sustainability. As we continue to develop and implement these technologies, we move closer to a future where clean, efficient, and reliable energy is available to all. Section 9. Conclusion: the future of steam. So there you have it, the Clausius Rankine Cycle, a cornerstone of modern power generation. From the humble steam engine to the ultra-supercritical power plants of today, this cycle has powered our world for generations. As we move towards a cleaner and more sustainable energy future, the Clausius Rankine Cycle will continue to play a vital role. With ongoing innovation and a commitment to efficiency, steam power has the potential to remain a key player in the global energy mix for years to come. Pumps are everywhere. We may not see them, but they're working hard behind the scenes. They move fluids, plain and simple. Water, oil, chemicals, you name it. Without pumps, our world would grind to a halt. Think about it. Your morning shower? Pumps get the water flowing. Filling up your gas tank? Pumps are on the job. Even that cold beer you're looking forward to, pumps played a part in getting it to you. Industries rely on pumps like a fish needs water. Water treatment plants use them to move millions of gallons. Oil refineries depend on them to transport crude. Power plants use them to circulate cooling water. The list goes on and on. Simply put, pumps are the unsung heroes of our modern world. They keep things moving, literally. And without them, life as we know it would be a whole lot different. Just like there's no one-size-fits-all tool, there's a whole mess of pumps out there, each with its own unique design and purpose. Each one designed for a specific job, tailored to meet particular needs and challenges. Some move thin fluids like water or oil, while others handle thick goop like sludge or paste. Let's break it down and see what makes each type special. First up, we got centrifugal pumps. These are the workhorses of the pump world, used in a variety of applications. They use a spinning impeller to create suction and move fluids efficiently, making them ideal for many tasks. You'll find these guys in everything from home water systems to massive industrial plants, handling everything from clean water to chemicals. Then there's positive displacement pumps. These are designed for precision and power. These bad boys use a chamber to trap a fixed volume of fluid and then force it out, ensuring a consistent flow. Lobe pumps, gear pumps, diaphragm pumps, they all fall under this category, each with its own unique mechanism and application. They're great for handling thicker fluids and precise dosing, making them essential in industries like food processing and pharmaceuticals. And we can't forget about the big boys, the axial flow pumps. These are designed for moving large volumes of fluid. These use a propeller-like design to move huge volumes of fluid at low pressure. Think dams, irrigation systems, that kind of scale. Companies like Grundfos, KSB, and Flowserve, they're the big dogs in the pump world. They're constantly innovating, pushing the boundaries of what's possible. Building pumps that are more efficient, more reliable, and built to last, ensuring that every job gets done right. Pumps are tough, no doubt about it, but even the toughest pump ain't invincible. Corrosion is a silent enemy, eating away at metal parts and shortening a pump's lifespan. Think of it like rust on your truck. Leave it unchecked, and eventually you got a hole. Same goes for pumps. Corrosion can create leaks, reduce efficiency, and even cause catastrophic failures. That's why pump manufacturers are always looking for ways to combat corrosion. They use special alloys, coatings, and even design pumps with sacrificial anodes that corrode first, protecting the critical parts. Fighting corrosion ain't cheap, but it's a whole lot cheaper than replacing a pump that's failed prematurely. And when you're talking about pumps that keep our water clean and our factories running, it's a fight worth fighting. Here's another thing that can spell trouble for pumps: cavitation. Sounds kinda cute, right? Like something you'd see in a fish tank. But in the pump world, cavitation is anything but cute. Basically, it's when bubbles form in a fluid due to pressure changes. These bubbles implode with incredible force, and when they do, they can damage the pump impeller and other internal parts. Think of it like tiny explosions going off inside your pump. Not good. Cavitation can lead to noise, vibration, reduced efficiency, and ultimately, pump failure. To prevent cavitation, engineers need to make sure the pump is properly sized for the application and that the fluid has enough pressure at the suction side. It's all about maintaining a smooth, consistent flow. Section 5. Sealing the deal, keeping fluids contained. Pumps move fluids, but they gotta keep them contained too. This is crucial in any system where fluid transfer is involved, whether it's water, oil, chemicals, or any other liquid. That's where seals come in. Seals are essential components that ensure the fluid stays where it's supposed to be, preventing leaks and maintaining system integrity. These little guys prevent leaks and ensure the pump operates efficiently. Without proper sealing, the efficiency of the pump drops significantly, leading to potential system failures. Without them, you got a big wet mess on your hands. Leaks can cause not only operational issues, but also safety hazards, especially in industrial settings. There are all sorts of seals out there, from simple O-rings to complex mechanical seals. Each type has its own specific application and benefits. The type of seal used depends on the fluid being pumped, the pressure, the temperature, and the environmental conditions. Choosing the right seal is critical for optimal performance, and a bunch of other factors. Engineers and technicians must carefully consider all these variables when selecting seals. Mechanical seals are like the heavy-duty option. They are designed to handle more demanding conditions and provide a more reliable seal. They use two faces that rotate against each other, creating a tight seal that can withstand high pressures and temperatures. Creating a seal that can handle high pressures and temperatures. This makes them ideal for heavy-duty industrial applications. They're often used in industrial applications where leaks can't be tolerated. Their robust design ensures long-term reliability and safety. Then there's magnetic drive pumps. These are kinda cool. They offer a unique solution to the sealing problem. Instead of a direct mechanical connection between the motor and the impeller, they use magnets to transmit torque. This innovative design reduces the risk of leaks significantly. This eliminates the need for a shaft seal, which is often the weakest point in a pump system, making them ideal for handling hazardous or corrosive fluids. These pumps are perfect for environments where safety and reliability are paramount. Section 6, the thick and thin of it. Viscosity matters. Fluids come in all sorts of consistencies. From the thinnest liquids like water to the thickest like honey, each fluid has its own unique properties. Water is thin and flows easily. It moves quickly and doesn't require much effort to pour or pump. Honey, on the other hand, is thick and sticky. It moves slowly and requires more effort to handle. This difference in consistency is called viscosity, and it plays a big role in pump selection and performance. Think about it. The higher the viscosity, the thicker the fluid. Trying to suck honey through a straw is a lot harder than sucking water. The resistance you feel is due to the higher viscosity of honey. The same principle applies to pumps. Pumps need to work harder to move thicker fluids. Thick, viscous fluids require more power to move than thin fluids. This means more energy consumption and potentially more wear and tear on the pump. When engineers design a pump system, they gotta factor in the viscosity of the fluid. They need to ensure the pump can handle the specific type of fluid it will be moving. They need to select a pump that can handle the thickness and make sure the pipes are sized appropriately to minimize pressure loss. Proper design ensures efficiency and longevity. Getting the viscosity right is crucial for pump efficiency. A well-matched pump and fluid can save energy and reduce maintenance costs. A pump that's not designed for the fluid it's handling will have to work harder, use more energy, and wear out faster. This can lead to frequent breakdowns and costly repairs. It's like trying to run a marathon in flip-flops. The wrong equipment for the job makes everything harder and less efficient. Section 7. Navigating the pipeline's pressure loss in circuits. Once a pump has moved a fluid, it needs to get where it's going. That's where pipes come in. But here's the thing. Pipes ain't frictionless. As fluid flows through them, it loses pressure. Think of it like a water slide. The longer and windier the slide, the slower you go at the bottom. The same goes for pipes. The longer the pipe and the more bends and fittings it has, the more pressure the fluid loses along the way. Engineers need to account for this pressure loss when designing pump systems. They use calculations to determine the right pipe size, material, and layout to minimize pressure drops and ensure the fluid reaches its destination with enough pressure. This is especially important in applications where maintaining a specific pressure is critical, like in irrigation systems or industrial processes. Too much pressure loss, and the system won't work properly. Section 8. Innovations in pumps. A look at the leading edge. The pump industry ain't standing still. Companies are constantly innovating, developing new technologies to make pumps more efficient, reliable, and environmentally friendly. One big area of focus is energy efficiency. Pumps are big energy consumers, so even small improvements in efficiency can lead to significant cost savings and reduced emissions. Manufacturers are using computer modeling and advanced materials to optimize pump designs, reducing friction and turbulence. They're also incorporating variable speed drives that allow pumps to operate at the most efficient speed for the application. Another area of innovation is smart pumps. These pumps use sensors and software to monitor performance, detect problems early on, and adjust operation automatically. Think of it like having a mechanic built right into your pump. These advancements are helping to make pumps more sustainable and cost-effective, which is good news for both businesses and the environment. Section 9. Conclusion pumps, the unsung heroes of modern life. So there you have it. Pumps, the unsung heroes of our modern world. They keep our water flowing, our factories humming, and our beers cold. They may not be glamorous, but they're essential. Next time you take a shower, fill up your gas tank, or enjoy a cold drink, take a moment to appreciate the humble pump. It's working hard behind the scenes, making your life a little bit easier. And thanks to the hardworking folks in the pump industry, these vital machines are only getting better. With their focus on innovation and sustainability, they're ensuring that pumps continue to play a critical role in our world for generations to come. Today we're talking about boilers, the unsung heroes of many power plants. These massive machines are crucial for the generation of electricity. These mighty machines are like giant kettles, but instead of making tea, they generate the high-pressure steam that spins turbines and creates electricity. Imagine a kettle on your stove, but on a much larger scale and with a lot more power. You see, most power plants rely on the power of steam. This steam is produced by heating water in the boilers, and it's the driving force behind the turbines. It all starts with water. Clean, treated water is essential for the efficient operation of boilers. Without it, the entire process would come to a halt. Boilers heat that water, turning it into steam. This transformation is a critical step in the energy production process. The water is heated to extremely high temperatures, creating steam that is under immense pressure. This steam is what packs the punch. It has incredible energy. The high-pressure steam is then directed towards the turbines, where it unleashes its power. This energy allows it to push the blades of giant turbines. These turbines are massive, with blades that can be several meters long. As the steam pushes the blades, it causes the turbines to spin at high speeds. And guess what? Spinning turbines mean we can generate electricity. Pretty cool, right? The spinning motion of the turbines is converted into electrical energy, which is then transmitted through power lines to our homes and businesses. So the next time you flip a light switch, remember the incredible journey of steam and turbines that makes it all possible. Okay, so how do boilers actually work? Let's dive into the fascinating world of steam power and uncover the magic behind these industrial giants. Picture this. Water enters the boiler and flows through a network of tubes. These tubes are meticulously designed to maximize the surface area for heat transfer, ensuring that every drop of water gets its fair share of heat. These tubes are surrounded by a raging fire, fueled by coal, natural gas, or even biomass. Talk about hot stuff. The choice of fuel can vary depending on the boiler's design and the availability of resources, but the goal remains the same. Generate intense heat. As the water travels through the hot tubes, it absorbs an incredible amount of heat. This process is known as heat exchange, and it's the heart of the boiler's operation. The efficiency of this heat exchange determines how effectively the boiler can convert water into steam. This heat transforms the water from its liquid state into steam, lots and lots of steam. The transformation is almost magical, as the water molecules gain energy and break free from their liquid bonds, turning into a powerful gas. But it's not just about making steam, it's about making it powerful. The steam generated inside the boiler is under high pressure, which gives it the energy needed to perform work, whether it's driving a turbine or heating a building. This is where pressure comes in. The boiler is designed to withstand and control this pressure, ensuring that the steam is delivered at the right force and temperature for its intended use. Boilers are designed to handle incredible pressure, which superheats the steam, making it even more energetic. Superheated steam is steam that has been heated beyond its boiling point without increasing its pressure. This makes it an incredibly efficient and powerful medium for transferring energy. Now let's talk fuel. Boilers are pretty versatile when it comes to what they can use. Natural gas is a popular choice. It burns relatively cleanly and is easy to control. Biogas, made from decomposing organic matter, is another eco-friendly option. But wait, there's more. Some boilers are fueled by biomass like wood chips or agricultural waste. And yes, even coal. Though it's important to remember that burning coal releases more pollutants. The choice of fuel depends on factors like cost, availability, and environmental impact. Boilers come in all shapes and sizes, each with its own unique design. One common type is the fire tube boiler, where hot gases from the fire pass through tubes surrounded by water. Think of it like a straw running through a pot of water on the stove. Another type is the water tube boiler. Here, water flows through tubes surrounded by hot gases. This design is more efficient for generating high-pressure steam. We also have fluidized bed boilers, where fuel is suspended in a bed of hot, bubbling material. This allows for more efficient and cleaner combustion. Section 5. Keeping boilers running smoothly. Tackling the tough stuff. Running a boiler isn't always smooth sailing. These massive machines are the heart of many industrial operations, and their smooth functioning is critical. Like any complex machine, they can experience wear and tear. Over time, the mechanical parts can degrade, leading to inefficiencies and potential breakdowns. One common issue is scaling mineral deposits that build up inside the tubes. These deposits can come from the minerals present in the water used in the boiler. It's like the gunk you get in your tea kettle. Over time, this buildup can become quite significant. Scaling reduces heat transfer and can lead to overheating. When the heat transfer is compromised, the boiler has to work harder, which can cause further damage. Then there's corrosion, which weakens the boiler materials over time. Corrosion can be caused by various factors, including the chemical composition of the water and the operating conditions of the boiler. And let's not forget about thermal fatigue, caused by repeated heating and cooling cycles. This constant expansion and contraction can create cracks and weaken the structure of the boiler. To keep boilers in tip-top shape, regular maintenance is crucial. This includes routine inspections, cleaning, and replacing worn-out parts. Think of it like taking your car in for a tune-up. Just as you wouldn't drive your car for years without a checkup, boilers need the same kind of attention to ensure they run efficiently and safely. Advanced diagnostic tools and techniques can help identify potential issues before they become major problems. By catching these early, you can save time, money, and avoid unexpected downtime. Collaboration among the maintenance team is also key. Sharing knowledge and experiences can lead to better problem-solving and more effective maintenance strategies. With the right approach, boilers can run smoothly and efficiently, providing reliable service for years to come. It's all about tackling the tough stuff head-on and staying proactive. Section 6. Cleaning up the act. Reducing emissions from boilers. While boilers are essential for power generation, we can't ignore their environmental impact. Burning fossil fuels releases greenhouse gases like carbon dioxide, which contribute to climate change. That's why it's so important to find ways to reduce emissions. One promising technology is carbon capture and storage, which captures carbon dioxide from the exhaust gases and stores it underground. We also use filters and scrubbers to remove other pollutants like sulfur dioxide and particulate matter. These technologies help make power generation cleaner and more sustainable. Remember how we talked about pressure? Boilers are designed to create steam at incredibly high pressures. Why is this important? Because high-pressure steam carries more energy, which translates to more power output from the turbines. To achieve these high pressures, boilers use special components like superheaters, which further heat the steam after it's been generated. They also have economizers, which preheat the water before it enters the boiler, improving overall efficiency. And, of course, pressure control valves keep everything running safely within the desired range. Now, you might be wondering, What about the water that condenses back from steam? That's where steam traps come in. These ingenious devices automatically remove condensate from steam lines, ensuring that only dry, high-energy steam reaches the turbines. There are different types of steam traps, each with its own mechanism: mechanical, thermodynamic, and thermostatic. Choosing the right type depends on factors like pressure, flow rate, and application. Whatever the type, steam traps play a vital role in maintaining efficiency and preventing damage to equipment. Once the high-pressure steam is ready, it's time to deliver it to the turbines. This is done through a network of heavily insulated pipes. Insulation is key here, as it prevents heat loss and maintains the steam's energy as it travels. Along the way, engineers carefully monitor pressure and temperature to ensure everything is running smoothly. They also take steps to prevent condensate from forming in the pipes, as this can reduce efficiency and even damage equipment. Remember, it's all about delivering that powerful steam to the turbines. As we look to the future, boilers will continue to play a vital role in our energy mix. But they need to evolve to meet the demands of a changing world. That means finding ways to make them even more efficient, reducing their environmental impact, and exploring alternative fuels. From advanced materials to smart control systems, innovations are constantly being made to improve boiler technology. By embracing these advancements and investing in research and development, we can ensure that boilers remain a cornerstone of a cleaner, more sustainable energy future. And that's something we can all feel good about. The power of turbines. Steam turbines are a marvel of modern engineering, transforming the energy of steam into mechanical power that drives our world. Steam turbines are remarkable machines. They consist of numerous intricate components, each playing a crucial role in the conversion process. They harness the energy of steam and transform it into mechanical power. This transformation is a complex yet fascinating process that involves several stages. This power then drives generators, producing electricity for homes and industries. The electricity generated is transmitted through power lines to reach various destinations. Steam turbines are essentially sophisticated heat engines. They operate on principles that have been refined over decades of technological advancements. They operate on the principle of converting thermal energy into kinetic energy. This conversion is fundamental to the turbine's operation and efficiency. This is achieved by expanding high-pressure, high-temperature steam through a series of carefully designed blades. These blades are engineered to maximize energy extraction. The process begins with water being heated to its boiling point. This produces steam. The steam is then collected and directed towards the turbine. The steam, now at high pressure and temperature, is directed through nozzles. These nozzles play a critical role in controlling the steam flow. These nozzles are designed to accelerate the steam flow. The acceleration increases the steam's kinetic energy, which is essential for the next stage. As the high-velocity steam expands through the turbine, it impacts the blades. The impact forces the blades to move, transferring energy to the turbine shaft. This impact causes the turbine shaft to rotate at high speeds. The rotation is smooth and continuous, ensuring a steady output of mechanical power. This rotational energy is the heart of the turbine's power. It is this energy that is harnessed to perform various tasks. It can be used to drive a wide range of machinery. From industrial machines to household appliances, the applications are vast. The most common application is in electricity generation. Power plants around the world rely on steam turbines to produce the electricity we use every day. Here, the turbine shaft is connected to a generator. The generator is a crucial component that converts mechanical energy into electrical energy. The generator then converts the mechanical energy into electrical energy. This conversion is vital for the distribution of power to homes and industries. This process highlights the vital role steam turbines play in our modern world. Without them, our ability to generate and distribute electricity would be severely limited. Steam turbines vary significantly in size and power output. This diversity allows them to be used in a wide range of applications, from small-scale industrial processes to large power plants. They range from small units used in industrial processes to massive machines found in power plants. Each type is designed to meet specific energy needs. Despite their differences, they all share the same fundamental principle: harnessing the energy of steam to generate power. This principle is the cornerstone of their operation and efficiency. Powering the world. Applications of steam turbines. Steam turbines are essential components of many industries. Their primary application is in power generation. Power plants, both nuclear and fossil fuel powered, rely heavily on steam turbines. These turbines convert the heat generated from nuclear reactions or the combustion of fossil fuels into electricity. Beyond power generation, steam turbines are widely used in various industrial processes. They provide mechanical power for pumps, compressors, and other heavy machinery. Industries like oil and gas, chemical processing, and paper manufacturing rely on steam turbines for their operations. The versatility of steam turbines stems from their ability to operate efficiently across a wide range of sizes and power outputs. This adaptability makes them suitable for both large-scale power generation and smaller-scale industrial applications. The use of steam turbines in combined cycle power plants further enhances their efficiency. In these plants, the exhaust heat from the gas turbine is utilized to generate steam. This steam then powers a steam turbine, effectively extracting more energy from the same fuel source. This combined cycle approach significantly improves the overall efficiency of power generation. The widespread use of steam turbines across various sectors underscores their importance in global energy production and industrial processes. From steam to spin. The expansion process. The heart of a steam turbine's operation lies in the expansion of steam. This is where the magic happens, transforming the potential energy stored in steam into a mechanical work. This process converts the thermal energy stored in the steam into kinetic energy, which ultimately drives the turbine. The transformation is both intricate and fascinating, involving precise engineering and physics. The steam, at high pressure and temperature, enters the turbine through stationary nozzles. These nozzles are the gatekeepers, controlling the flow and direction of the steam. These nozzles are meticulously designed to accelerate the steam flow. The design and precision of these nozzles are critical, as they ensure the steam reaches the optimal speed and direction. As the steam expands through the nozzles, its pressure decreases while its velocity increases. This expansion is a key part of the process, converting pressure energy into kinetic energy. This high-velocity steam then impinges upon the turbine blades, which are mounted on a rotating shaft. The impact of the steam on the blades is what drives the rotation of the shaft. The shape of the blades is crucial. They are designed to efficiently convert the kinetic energy of the steam into rotational energy. The engineering behind these blades is a marvel of modern technology. They are designed to efficiently convert the kinetic energy of the steam into rotational energy. The blade's curvature and angle are optimized to capture the maximum amount of energy from the steam. The curved shape of the blades causes the steam to change direction as it passes through them. This change in direction is essential for transferring the steam's energy to the blades. This change in momentum imparts a tangential force on the blades, causing the shaft to rotate. The rotation of the shaft is what ultimately generates mechanical power. The expansion process is not a single-step event. It is a continuous process that occurs in multiple stages, each stage extracting more energy from the steam. It occurs across multiple stages within the turbine. Each stage is carefully designed to maximize energy extraction and efficiency. Each stage consists of a set of stationary nozzles and a row of moving blades. The interaction between these components is what drives the turbine's operation. The steam progressively expands through these stages, with its pressure decreasing and velocity increasing at each stage. This staged expansion is crucial for maintaining efficiency and power output. This multi-stage expansion process ensures maximum energy extraction from the steam, enhancing the turbine's overall efficiency. By carefully managing the expansion process, engineers can optimize the performance and longevity of the turbine. A symphony of stages: high, medium, and low-pressure turbines. These turbines work in harmony to convert steam energy into mechanical energy, which is then used to generate electricity. Each stage plays a crucial role in ensuring the efficiency and effectiveness of the entire system. To maximize energy extraction from steam turbines often incorporate multiple turbine sections. This multi-stage approach allows for a more efficient conversion of steam energy into mechanical energy, as each section is designed to handle specific pressure and temperature ranges. These sections, known as high pressure, intermediate pressure, and low pressure turbines, are arranged in series. This arrangement ensures that the steam's energy is gradually extracted in stages, optimizing the overall efficiency of the turbine system. Each section is optimized for a specific range of steam pressure and temperature. Engineers meticulously design and maintain these sections to ensure they operate at peak performance, maximizing energy extraction at each stage. The high-pressure turbine receives the highest pressure steam directly from the boiler. This steam, at its highest energy state, is used to drive the first stage of the turbine, initiating the energy conversion process. As the steam expands through the high-pressure turbine, its pressure and temperature drop. This expansion process converts the steam's thermal energy into mechanical energy, which is then used to generate electricity. The partially expanded steam then enters the intermediate pressure turbine, where further expansion occurs. This stage continues the process of energy extraction, utilizing the remaining pressure and temperature of the steam. Finally, the steam, now at low pressure, enters the low-pressure turbine for the final stage of expansion. This stage extracts the last bit of usable energy from the steam before it exits the turbine system. This serial arrangement allows each turbine section to operate at its peak efficiency. By dividing the energy extraction process into multiple stages, the system can handle varying steam conditions more effectively. The high-pressure turbine, designed for high pressures, extracts energy from the steam's initial high-energy state. This stage is crucial for setting the foundation for the subsequent stages of energy extraction. The intermediate pressure turbine handles the steam at intermediate pressures, continuing the energy extraction process. This stage ensures that the steam's energy is efficiently converted as it moves through the system, while the low-pressure turbine extracts the remaining energy from the low-pressure steam. This final stage is essential for maximizing the overall efficiency of the turbine system. The exhaust steam from the low-pressure turbine at very low pressure is then condensed back into water in a condenser. This condensation process is vital for maintaining the closed-loop system of the steam cycle. This condensed water is then pumped back to the boiler, completing the steam cycle. The closed-loop system ensures that the water is reused efficiently, reducing waste, and improving the overall sustainability of the power generation process. This multi-stage arrangement and closed-loop system contribute significantly to the high efficiency of steam turbines and power generation. By optimizing each stage of the process, engineers can ensure that the maximum amount of energy is extracted from the steam, making steam turbines a vital component of modern power plants. Have you ever wondered what happens after steam spins those giant turbines? That's where the condenser comes in. It's like the heart of a power plant, keeping the whole system pumping. So picture this. Super hot, high-pressure steam has just done its job pushing the turbine blades. Now it needs to cool down and transform back into water. That's exactly what the condenser does. It's a giant heat exchanger that converts exhaust steam back into liquid water, ready for another cycle. This process isn't just about cooling down the steam, it's about efficiency too. By condensing the steam back into water, we can reuse it, saving energy and resources. Plus, it creates a low-pressure environment that helps the turbine do its job even better. Stay tuned to learn more about how these amazing machines work. Remember how I said condensers are all about efficiency? Well, it's true. They play a key role in making power plants more sustainable and environmentally friendly. Here's the deal. By capturing and reusing the exhaust steam, condensers enable a closed-loop system. This means less water is wasted compared to systems that just vent steam into the atmosphere. In a world facing water scarcity, that's a big deal, and it gets even better. Remember that low-pressure environment the condenser creates? This actually allows the turbine to extract more energy from the steam, boosting the overall efficiency of the power plant. More power, less fuel. That's what we call a win-win. So not only do condensers save water, but they also help us squeeze every bit of energy out of our fuel sources. That means fewer emissions and a cleaner planet. Now that's what I call science making a difference. All right, science enthusiasts, let's get into the nitty-gritty of how condensers actually work. It all boils down to some fundamental principles of thermodynamics and clever engineering. Inside the condenser, the exhaust steam from the turbine encounters a network of cold tubes. These tubes are usually filled with cooling water, which we'll talk more about later. As the hot steam comes into contact with these cool surfaces, it loses its heat energy and begins to condense back into liquid water. But here's the really cool part. Condensers operate under a vacuum. You see, reducing the pressure inside the condenser dramatically lowers the boiling point of water. This means the steam condenses more readily at lower temperatures, making the whole process much more efficient. Creating and maintaining this vacuum is crucial for optimal condenser performance. In the next section, we'll explore some of the challenges of operating in this low-pressure environment. Operating a condenser under a vacuum may sound simple, but it comes with its own set of challenges. Imagine trying to keep a giant container airtight while maintaining a pressure lower than the atmosphere. One of the main difficulties is ensuring effective heat transfer at these low pressures. The temperature difference between the cooling water and the steam is smaller, which can make the condensation process less efficient. Leaks are another major concern. Even the tiniest air leak can disrupt the vacuum, reducing condenser efficiency and potentially damaging equipment. That's why power plants have strict maintenance procedures to detect and repair leaks promptly. And then there's cavitation, a phenomenon that can occur when the pressure inside the condenser drops too low. This can cause the formation of vapor bubbles in the cooling water, which can damage the condenser tubes and reduce heat transfer efficiency. Despite these challenges, engineers have developed ingenious solutions to ensure condensers operate reliably and efficiently. Section 5. Types and sizes. Different condensers for different power plants. Just like power plants come in different sizes and types, so do condensers. The design and size of a condenser depend on factors like the plant's capacity, the type of steam turbine used, and the available cooling water source. One common type is the surface condenser, where the steam and cooling water don't directly mix. Instead, the steam condenses on the outer surface of tubes carrying the cooling water. Another type is the direct contact condenser, where the steam and cooling water mix directly. This type is simpler in design but can be less efficient and pose challenges in maintaining water purity. The size of a condenser is directly related to the power plant's capacity. Larger power plants require larger condensers to handle the massive volumes of exhaust steam produced. It's all about scaling up to meet the energy demands. In the next section, we'll explore the different methods used to keep those condensers cool and running smoothly. Section 6. Keeping it cool cooling methods for power plant condensers. We've talked about how condensers use cooling water to condense steam, but where does that water come from? Well, power plants use various cooling methods, each with its own advantages and challenges. One common method is once-through cooling, where water is drawn from a nearby river, lake, or ocean, circulated through the condenser, and then discharged back into the source. While this method is relatively simple, it can impact aquatic life due to the temperature change of the discharged water. Another method is using cooling towers, which are those iconic structures you often see next to power plants. Cooling towers evaporate a small portion of the circulating water, cooling the remaining water, which is then reused in the condenser. This method reduces water consumption but requires energy for fan operation. Choosing the right cooling method depends on factors like water availability, environmental regulations, and cost effectiveness. It's all about finding the balance between energy production and environmental responsibility. Section 7. Nuclear power and water. Special considerations for safety. When it comes to nuclear power plants, water plays an even more critical role. Not only is it used for cooling the condenser, but it's also vital for moderating the nuclear reaction itself. This means safety is paramount when it comes to water systems in nuclear plants. One crucial aspect is isolating the water used in the reactor from the water used in the condenser. This prevents any potential contamination of the reactor's cooling system, ensuring the safe operation of the plant. Nuclear plants also have robust safety measures in place to handle condenser-related events. For example, in case of a turbine trip, Auxiliary condensers or steam dump systems are activated to condense the excess steam and prevent pressure buildup. Safety is the top priority in any power plant, but the stakes are even higher in nuclear facilities. That's why multiple layers of safety systems and protocols are in place to prevent accidents and protect both people and the environment. Section 8. Material Matters. Ensuring condenser longevity and performance. Condensers may seem like simple devices, but they operate under harsh conditions that can take a toll on their materials. From high temperatures and pressures to corrosive chemicals and biological growth, condensers face a constant barrage of challenges. One common issue is scaling, where dissolved minerals in the cooling water precipitate onto the condenser tubes, forming an insulating layer that reduces heat transfer efficiency. Regular cleaning and water treatment are essential to combat scaling. Corrosion is another persistent problem, especially in coastal power plants where salt water is used for cooling. Corrosion can weaken the condenser tubes, leading to leaks and reduced lifespan. Using corrosion-resistant materials and protective coatings helps mitigate this issue. Ensuring condenser longevity requires a multi-pronged approach, including careful material selection, regular maintenance, and effective water treatment. It's all about staying one step ahead of potential problems to keep those condensers running smoothly. Section 9. The crucial vacuum sealing, maintenance, and emergency procedures. Remember that crucial vacuum we talked about earlier? Well, maintaining that vacuum is essential for optimal condenser performance and overall power plant efficiency. Sealing is paramount. Even the smallest air leak can disrupt the vacuum, reducing condensation efficiency and potentially causing damage. Power plants use a variety of sealing techniques, from gaskets and O-rings to vacuum pumps and leak detection systems, to keep that precious vacuum intact. Regular maintenance is key to ensure those seals remain effective. Inspections, cleaning, and timely replacement of worn-out components are all part of the routine to prevent leaks and maintain optimal vacuum pressure. And in case of emergencies like a sudden turbine shutdown, power plants have procedures in place to handle the rapid condensation of steam. These may include diverting steam to auxiliary condensers or venting it safely to the atmosphere to prevent pressure buildup and potential damage. Maintaining the condenser's vacuum is an ongoing effort, requiring vigilance, proactive maintenance, and well-defined emergency procedures. It's all about keeping that pressure low and that efficiency high. Section 10. Recap the unsung heroes of efficient power generation. So there you have it, folks. We've journeyed through the fascinating world of power plant condensers, from their basic function to the challenges they face and the ingenious solutions engineers have developed. These often overlooked components play an absolutely crucial role in ensuring the efficient and sustainable operation of power plants worldwide. They're the unsung heroes of electricity generation, quietly working behind the scenes to keep the lights on while minimizing our environmental impact. Whether it's a conventional power plant, a renewable energy facility, or a nuclear power station, condensers are essential for maximizing energy efficiency, conserving water, and enabling a cleaner energy future. So the next time you flip on a light switch, take a moment to appreciate the science and engineering that went into making that possible, including the humble yet mighty condenser. Vast cosmic ocean, civilizations are often compared by their technological prowess. One measure of this is the Kardashev scale, a system that categorizes civilizations by their energy consumption. A Type 1 civilization, the first rung on this ladder, represents a species that has mastered the energy output of its home planet. Imagine harnessing the full power of our sun on Earth. That's the scale of a Type 1 civilization. Becoming a Type 1 civilization is no small feat. It demands an enormous and sustainable energy supply. Think about our growing population, expanding industries, and reliance on technology. Now, amplify that demand exponentially as we strive for planetary-scale energy solutions. This is the challenge and the promise of a Type 1 future. We need power sources that are not only abundant, but also kind to our planet. Steam turbines, the workhorses of our current energy infrastructure, will undoubtedly play a crucial role in our Type 1 energy transition. However, To remain relevant, they must evolve and adapt. Imagine turbines crafted from advanced materials, able to withstand higher temperatures and pressures. Picture systems so efficient that energy loss is minimized, maximizing the power output from every drop of steam. Steam turbines excel at providing a constant, reliable flow of energy, what we call baseload power. Think of the steady hum of a power plant keeping the lights on throughout the day and night. But they can also be agile, ramping up quickly to meet surges in demand, known as peak load. This adaptability makes them valuable assets in a future energy grid characterized by fluctuating renewable sources. Section 5. The Energy Symphony. Steam in a diverse orchestra. The future of energy is not a solo act, it's a symphony. Steam turbines won't be the only instruments in this orchestra. Solar, wind, geothermal, and even fusion power will all play their parts. Imagine steam turbines working in concert with these renewable sources, smoothing out the intermittencies of solar and wind, providing a reliable backbone for a cleaner, more sustainable energy future. Section 6. Engineering Evolution, a glimpse into tomorrow's turbines. The steam turbines of tomorrow will be marvels of engineering. Nanotechnology could lead to materials with unprecedented strength and heat resistance. Advanced control systems, driven by artificial intelligence, will optimize performance and predict maintenance needs. These advancements will not only boost efficiency, but also extend the lifespan of these energy giants, making them even more valuable in a resource-constrained world. Section 7. The Sustainability Equation, Balancing Power and Planet. In our quest for sustainable energy, we face the challenge of balancing the immense power needs of our modern world with the urgent necessity to protect our planet. This delicate balance is at the heart of the sustainability equation. The environmental impact of steam turbines, particularly those reliant on fossil fuels, cannot be ignored. These turbines, while efficient in generating power, release significant amounts of carbon dioxide and other greenhouse gases into the atmosphere. This contributes to global warming and climate change, posing a serious threat to our environment and health. But there are solutions. Carbon capture and storage technologies can trap emissions before they reach the atmosphere. These technologies work by capturing carbon dioxide produced by power plants and other industrial sources, then transporting it to a storage site where it is injected deep underground. This prevents the carbon dioxide from contributing to the greenhouse effect, helping to mitigate climate change. Shifting towards cleaner fuels like biofuels or even hydrogen can significantly reduce the carbon footprint. Biofuels are produced from renewable resources such as plants and algae, and they emit less carbon dioxide when burned compared to fossil fuels. Hydrogen, on the other hand, produces only water vapor when used as a fuel, making it an incredibly clean energy source. The goal is clear: to harness the power of steam turbines while minimizing their impact on the planet we are striving to power. By integrating advanced technologies and cleaner fuels, we can create a more sustainable energy future. This requires innovation, investment, and a commitment to environmental stewardship. Together, we can achieve a balance that ensures both our energy needs and the health of our planet are met. Section 8. A glimpse into the future grid. Steam's enduring role. Visualize a future energy grid where power flows from diverse sources. Imagine a world where our energy needs are met by a harmonious blend of technologies, each contributing its unique strengths to the grid. Solar farms bask in the sun's energy, converting sunlight into electricity with remarkable efficiency. These vast fields of solar panels capture the sun's rays, turning them into a reliable source of power. Wind turbines dance in the breeze, harnessing the power of the wind to generate clean, renewable energy. These towering structures with their graceful blades are a testament to our ability to innovate and adapt. And strategically placed steam power plants provide stability and balance. These plants, often overlooked, play a crucial role in ensuring that the grid remains stable, especially during times when renewable sources are less reliable. This interconnected system, a testament to human ingenuity, seamlessly integrates various energy sources. It allows for a dynamic and flexible approach to energy management, adapting to fluctuations in supply and demand with ease. Ensuring a constant flow of power while minimizing our reliance on any single source, this grid is designed to be resilient. It can withstand disruptions and continue to provide power, even in the face of challenges. Paving the way for a more resilient and sustainable energy future, this advanced grid represents the pinnacle of our efforts to create a cleaner, more efficient world. It is a vision of what is possible when we combine technology, innovation, and a commitment to sustainability. Section 9. Navigating the challenges ahead: water, fuel, and innovation. The path to a steam-powered Type 1 civilization is not without its obstacles. Water, essential for steam generation, is a precious resource becoming increasingly scarce in many parts of the world. Finding sustainable fuel sources to power these turbines is another hurdle. These challenges demand innovation, pushing us to explore alternative cooling methods, develop more efficient water usage practices, and unlock the potential of new, cleaner fuels. Section 10. The Steam Turbine Legacy: Powering into the Future. As we stand on the cusp of a new era of energy, one thing is clear: the steam turbine, in its reinvented and reimagined form, will continue to play a vital role. The journey of the steam turbine began in the 19th century, revolutionizing the way we harness energy. From the early days of coal-powered behemoths to the sleek, efficient machines of today, the steam turbine has been at the heart of industrial progress. Today, it is not just about generating power. It is about doing so sustainably and efficiently. Engineers and scientists are constantly pushing the boundaries, developing new materials and technologies to make steam turbines more efficient and environmentally friendly. These titans of industry, once fueled by coal and driven by brute force, are evolving into sophisticated, sustainable powerhouses of the future. The integration of renewable energy sources, such as solar and wind, with steam turbine technology is paving the way for a cleaner, greener planet. Innovations in turbine design, such as the use of supercritical steam and advanced cooling techniques, are enhancing performance and reducing emissions. The future of steam turbines is not just about power generation. It is about creating a sustainable energy ecosystem that can support the needs of a growing global population. As we reach for the stars and strive for a Type 1 civilization, the hiss of steam, a sound synonymous with progress, will continue to echo in our ears, a reminder of humanity's relentless pursuit of a brighter energy future. The steam turbine's adaptability and resilience make it a cornerstone of our energy infrastructure. Whether on Earth or in the vast expanse of space, steam turbines will be integral to our quest for sustainable energy solutions. As we innovate and explore, the legacy of the steam turbine will continue to inspire and drive us towards a future where clean, efficient energy is accessible to all.